Let's parametrize circles next. So as I mentioned with lines, like, yeah, the moving point concept is cool, but maybe there's not as much motivation to go to parametric equations because you know everything about the Cartesian equation of a line. You spent years studying it in middle school and or high school. Whereas with circles, you do study circles. They gave you the equation for this. You might not even remember it because they didn't give it to you as much as they gave you the equation of a line. No one ever forgets y equals mx plus b for some reason. People forget everything else in high school math, but not that. So I don't know, maybe that's good. Maybe they teach one thing well. Anyways, but the only other thing you know about circles, and you spent probably more time on this, is trig. If you make an angle theta with the positive x-axis, then on the unit circle, this point is cosine theta comma sine theta. I think it's better to take that as the definition of cosine theta and sine theta, but that's a debate for another time. So this is actually a natural parametrization for the circle. I can parametrize this as the vector cosine theta sine theta, and like as I change the value of theta, this actually naturally moves around the circle. If I wanted to write parametric equations, I write x equals cosine theta, y equals sine theta. And if I plug those in, for sure, cosine squared theta plus sine squared theta equals 1, so that's good. That part works. So that's a natural parametrization for a circle. I can do funny things to it. I can do the same thing I talked about before. I can make it go faster. Cosine 3 theta, sine 3 theta. It's a little weird. So instead of like theta from 0 to 2 pi being 1 revolution, now theta from 0 to 2 pi over 3 is 1 revolution. I guess less than, not less than or equal to, unless I want to repeat that point. You guys don't necessarily have to worry about that a lot. But okay, so I can make it go faster. This is just literally the same thing, except I'm going around the circle 3 times faster. I can do, this is asinine, don't do this unless you want to be annoying, but like, if I switch these, sine theta, cosine theta, that's still a parametrization of the same circle. Don't do this unless you want to be super annoying. I would never do this to you. But what actually happens is just the x and y coordinates get swapped. So instead of starting here and going that way, I'm starting here and going that way. So that's still a parametrization of the circle. Okay, I don't mean don't ever do this, because if for some reason this is ever more convenient, please do this. I can start in different places. Like if I did cosine of theta plus pi over 3, comma sine of theta pi over 3, theta plus pi over 3. That's the same parametrization, except I started at that point. Started at that point, when theta is 0. Just make sure they're the same. I can't do pi over 3 and pi over 2, because now cosine squared theta plus pi over 3 plus sine squared theta plus pi over 2 is not 1, so now I've done something really weird. That's not the same thing. Okay, so that's still a circle. I can parametrize other circles. So like, here, let's go to the most general thing. Let's do x minus, no, let's not. Let's do an example first. Y plus 1 squared equals 9. This is a circle of radius 3 centered at the point 2 comma negative 1, if you remember your circle formula. Why is that? Because if I put in 2 comma negative 1, I get 0 on the left. So that's the center of the circle. And then 3 is the root of 9. Okay, so if I need to, what I need to do is shift that and stretch it. So I'm going to stretch it by multiplying both coordinates by 3. And then I'm going to shift it by adding 2 to the x and subtracting 1 from the y. So now the parametrization for this circle is that thing. I'm going to stretch it to have radius 3. I'm going to shift it to have center 2 comma negative 1. So that's not too bad. in all your 3D parametrizations, which we'll be doing. So we'll be doing 3D parametrizations, not just lines, but curves. And we'll have some funny curves, possibly. You won't necessarily have to graph them, so don't worry about that. But you can always shift them. You can always stretch them. You can stretch just one coordinate. By the way, you can think about that. What happens if you stretch just the x coordinate? So 2 cosine theta, sine theta. What shape is that? Think about that. That kind of thought process will be useful later in the course. Oh, let me tell you about a non-parametrization. So, like, remember when I said the lame parametrization is just set x equal to t? Let's try that. Set x equal to t. Then, okay, I'm going to try to solve for y. T squared plus y squared equals 1. Y squared equals 1 minus t squared. Y equals the square root of 1 minus t squared, right? And so I get the parametrization t, comma, the square root of 1 minus t squared, except that is wrong. That's very, very wrong because the y-coordinate, oh no, that's not what I wanted. The y-coordinate is always non-negative. So I don't get the whole circle. I only get the top half of the circle. Okay. Well, you can fix it, you say, right? Just put a plus or minus. It fixes everything. No, that's still bad. Because this is now, y is now, I need x and y to both be functions of t. So if I write this, y is not a function of t, because every value of t gives 2 values of y. So that's not a parametrization, period. It does give that whole curve. It gives the whole circle, but it's not a parametrization. So that's no good. There are, remember I said there were infinitely many parametrizations, and you can do things other than just go faster around the circle or start at different points. There are other parametrizations of the circle. This one's just not one of them. If you're interested in parametrizations, because it is fascinating, there's a really weird parametrization from this book, and I can't remember what it is, but the book, this is way beyond the scope of the course, but like if you're just interested in math, the first chapter of this book is super interesting to read. Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea. And it has some super interesting parametrizations, just even in 2 dimensions of curves. So that's fun. All right, that's all I need to say for now on parametrizations of circles.